welcome back to the last part of this rather long lecture. Now, we've been making an inventory of all the different ways that humans are making changes that result in some kind of radiative forcing at the Earth's surface. We talked about changes in the trace gases, we talked changes in the types of aerosols that are in the atmosphere. How about changes in land use? I mean, we take swampland and drain it and then grow crops on it or build neighborhoods on it. We drain lakes, we irrigate. We have all kinds of ways in which we can change the land surface's albedo, which changes the amount of radiation it's absorbing and reflecting. We have ways we change the evaporation rate at the surface by irrigating formerly dry land and so on. And this all has the potential to be changed as we do stuff at the surface of the Earth. Probably the one that has the largest climate impact is about the changes in albedo. The albedo of farmland is typically higher than the albedo of the land in its natural state. Now, admittedly, there is a whole lot of variability to that, but by and large, most ecosystems have a fairly low albedo. Certainly things like rainforests and grassland and pine forests and so on, they have very low albedo. That makes sense. The low albedo means it absorbs most of the sunlight. The plants that are active there are absorbing the sunlight and using that to make their food and so on. Whereas when we cut down a forest or we plow up a swamp or something like that and drain it, well, at least part of the year there is bare ground, like if we put fields there instead or whatever, and the bare ground is made of minerals. In general, bare ground has a higher albedo than a forest canopy or something like that, so it's reflecting more shortwave radiation. Also, generally speaking, like if it's cropland, there's usually bare ground between the plants. That also is usually more reflective than the leaves of the plant are, and so on. Overall, the idea of changing a natural environment into something used by man has a net effect, usually, of increasing its albedo. And of course, increasing the albedo of a surface means that it reflects more shortwave radiation, which means that it is now exerting a negative radiative forcing. Now, like for example, if you look at these fields here and so on, you can see that what would have otherwise been some kind of green forest or some kind of green grassland or something, still has some green in very dark places where it's absorbing a lot of sunlight, but you can see how as it's managed into these different kinds of field, there's bare ground, there's dead vegetation that also has a lot of our higher albedo. The net effect is to have a negative radiative forcing. It turns out to be about negative 0.2 watts per square meter when mankind changes the land use to, on average, to meet civilization's purposes. Another way in which we change the land surface has to do with the pollution that we give off, in particular black carbon. The black carbon aerosols do, over a period of time, settle by gravity out of the Earth's atmosphere. Like I said before, that process is actually called sedimenting. The black carbon sediments out of the atmosphere down onto the ground. Now, most of the time, we're not talking that much black carbon, and we're settling onto a surface that's already pretty dark. But when black carbon and other anthropogenic aerosols settle onto snowpack, we have a very dramatic change in the albedo of the snowpack. So, like, here, again, this isn't black carbon that's on the snow right here. This is, there's some bare ground cut off on the side of the picture here, but the bare ground was blowing dust onto the snow. And it has changed the albedo. That's a very dramatic example there, but all snow is slightly lower albedo than it would be without humans there because of the presence of black carbon aerosols settling on it. And the net effect of black carbon settling on snowpack and ice sheets and glaciers worldwide is to have a net radiative forcing increase of about positive 0.1 watts per square meter. It's fairly small, but it's positive. It is increasing the it is working to increase the temperature of the surface of the Earth. We have a lot of these different kinds of land use changes and so on. It's a little hard to make an inventory of all of them in a kind of just a little overview like this. Now, another whole set of radiative forcings that could be making changes to the climate of the Earth would be possible changes in the output of the sun. Now, we briefly touched on this back in the first module of the course. I mean, it would seem like this could be a very clear radiative forcing for the Earth. We could talk about, like, changing the output of the sun. Well, I mean, we're not changing. This would be a natural change as a way of driving the climate. And it is true that based on the sunspot cycle on the Earth, there is a change in the radiative forcing between the peak and the bottom of the sunspot cycle, which is about 11 years long. And the difference in the radiative forcing based on solar output is about a whole watt per square meter. And it is generally, I mean, well, it's positive if you compare like the period where there's the least solar output to the period that there is the most. But that's only over an 11-year cycle. I mean, it kind of cancels out. Over climate time scales, there are periods where the sun is more active, there are periods where the sun is less active. On a cycle of about 11 years, it pretty much is a wash. Over the 11-year solar cycle is pretty much a wash. Now, there is some reason to believe that there are like century-long trends or millennial trends in solar output. For example, there is some evidence to believe that the total output of the sun has been increasing since about 1750, with the total radiative flux increases due to the changes in the solar output being about 0.12 watts per square meter, which is not huge, but it's definitely a significant part of the total radiative forcing on the Earth. I mean, when people tell you that climate change is caused by changes in the sun, well, I mean, maybe a part of it anyway is. Now, certainly as we learned back in like the paleoclimate lecture, on the scale of like hundreds of millions of years as the sun has moved through its cycle, moved through its lifetime of being a main sequence star, yes, we have definitely seen how the sun can be driving climate. But if there is a trend like since the Industrial Revolution, it is smallish. Although in fairness, it is a trend towards making the planet warmer. It is a positive radiative forcing. So if you took all these radiative forcings that have been since the Industrial Revolution and you decided to add them all up, some of them were positives, some of them were negatives, which sounds like a great question to ask on a test. I could give you a whole list of different processes and you could tell me which ones were positive or which ones were negative radiative forcings. I like that idea. I should be writing that down. Anyway, if you add them all up, you get a net radiative forcing of the Earth's climate of about 1.6 watts per square meter. Between the greenhouse gases, the aerosols, the changes in the sun, the net radiative forcing has been about 1.6 watts per square meter. Way bigger than what like the sun is causing, smaller than what greenhouse gases are causing because we also have the aerosols and so on. Alright, 1.6 watts per square meter. That's about how much radiative forcing there should be driving the Earth's climate since the Industrial Revolution. Now, remember, if we actually used NASA's numbers, we came up with a close estimate, somewhere in the range of 0.6 to 0.9. Let's just go ahead and use the number 0.9. It came from a different textbook. That's fine. That is our current actual observed radiative imbalance. So why are these two numbers different? Well, because over the course of the last 100, 150 years or whatever, the planet has been getting warmer. And as the planet has been getting warmer, we have been compensating for that radiative forcing. At some point in the future, we will achieve a new temperature at which now there is no radiative forcing because we have increased the temperature of the Earth enough that now the temperature of the Earth is high enough, the Earth is emitting enough long-wave radiation that it balances this radiative forcing. But we're not there yet. In fact, we are only part of the way there. We are only about 9 of the 1.6 watts per square meter of total radiative forcing. We know now that there's still about 0.9 watts per square meter to go. That means that we have already warmed the planet enough to increase the flux of radiation off the surface of the Earth by 0.7 watts per square meter. Do you understand what I'm saying? What I'm saying is we have added enough anthropogenic processes to the climate to say that the total amount of change, the planet has to warm enough so that it is emitting 1.6 watts per square meter more than it is now. We know that we're actually out of balance by about 0.9 watts per square meter. That means we have already done some warming to cancel out that first part, that 0.7 watts per square meter. We just have this part that is left. If we stopped emitting greenhouse gases, the planet would keep warming until the surface of the Earth was emitting the full 1.6 watts per square meter worldwide, averaged over a year. Climate change is complicated stuff. I mean, we really would love to make this just all about greenhouse gases. But there's so much more to the puzzle. There's changes in solar output, changes in methane, changes in land use, changes in aerosols, and we're really barely even touching the business of clouds and moisture. We haven't even really gotten to the moisture aspects of climate change yet. Oh man, it's a big, complicated constellation of concepts, which is kind of what I'm vaguely trying to illustrate right there. All right, well, we have made it through this very long lecture. Let's answer 3 more quick questions before we're done. Question 13. Suppose a tropical rainforest is cut down to make room for a soybean field. Ugh, sounds horrible, but that actually happens every day in places like Brazil. Averaged over the course of the year, which has a higher albedo, the rainforest or a soybean field? Make a choice from those 2 options and get a little feedback before you move on to question 14.